Okay, so somebody should be saying, hey, what did that guy just say? So we had this pronouncement. We figured this out using Taylor series, which you don't really know about. I'm just asking you to believe that I know what I'm talking about. And we deduced this formula, e to the I theta equals cosine theta plus I sine theta. What is the norm of this? Well, I'll do this in a second. Basically, this is 1. This is on the unit circle. What if this particular case we're not on the unit circle here? How is this related to the complex plane in the proper coordinates? Well, we figured out that r, which is the modulus of this, which is 2 times the square root of 2, times cosine pi over 4, which was this angle, is in fact 2. This is the x component of the vector. We also figured out that r, without the I in there, and now let me pull this out, r sine pi over 4 was also 2. This is the y component of the vector. So this is y component. My writing's a little sloppy today. I'm excited because I like this stuff. However, we're in a complex plane. We need the yi component. So I put an I in there, and I put an I in there, and look at what we got. Z, the complex number z, can be written as r e to the I theta, which in this case is r times cosine theta plus I sine theta. This is really, really convenient, and it's amazing. So first off, let's do a couple of these so you can get comfortable with it. What is, suppose z equals 1 plus 3i. And incidentally, if you're wondering where I'm getting this, I'm 100% making these things up. I try as students crazy. They go, where's he pulling those numbers out of? That's just, I've been doing this for a while, and there are certain numbers that are convenient that show up a lot, so we pick them. In a very short time, they're going to say, write this as r e to the I theta. Well, how do you figure that out? Well, so r is the modulus, so r is equal to the modulus of z. R in this case is going to be the square root of a squared plus b squared is 1 squared plus 3 squared is the square root of 10. Let me make that a little better. Well, what's theta? How do we figure out theta? Well, if this is the x component and this is the y, remember that the tangent of theta is equal to y divided by x. So the tangent of theta in this case is 3 divided by 1. So that means that the arc tangent of 3 like this, is equal to, and I forgot my calculator again today. I'm going to stop and run to my office and get it. Bad me. Okay, so I went back to my office and got my calculator, and I have 3. I'm in degrees. I'm going arctangent, and this is like 71.565 degrees. So this is equal to what theta is, which is 71.565051118. I think I'm just going to go to 100's place again. We'll see how I feel. I feel like being very precise today. We'll just see. Well, so I have alpha defined here. Maybe I won't just write it in the equations everywhere. So how do we, oh no, I have to. Never mind. So how are we going to write this like this, which is this? This is the square root of 10 times e to the I. Theta is 71.565. I'll abbreviate it right here. This seems a more natural place. All right. And so this is equal to the square root of 10 times the cosine of 71.565 plus I times the sine of 71.565. Let's just do that so I can show you that this really works. So the cosine of this is 0.316 some change. I'll multiply it times 10 square root, and this is equal to 1 according to my calculator. plus, so now I'm going to do the sine of this. What do we got? 71.565 sine times the square root of 10, and this is, now because I have abbreviated here, this is 2.999999107. We know that this is 3. And it's written now like 1 plus I3, but we would write this as 1 plus 3I. I would write this way. This is just fine. There are some math instructors who really don't like that, but you'll figure it out. So that's all there is to it with this rather amazing formula. And let's think about what's going on here for a second about addition of complex numbers. Let's see what happens. And I'm going to pick a couple simple ones so it's easy enough to draw. And I'm going to write this formula up here. This is one you definitely want to know. So z can be written as r e to the I theta, where r is equal to the modulus of z and theta is equal to the arctangent of the y divided by x components of z. Right? Now I'm going to really try and make it semi-accurate, or accurate as I possibly can picture. So I'm going to draw it big. Here's 1, 2, 3. It's 1, 2, 3. 1, 2, 3. 1, 2, 3. So here's 1, 2, and 3. Yeah, here's I, 2I, and 3I. For the moment, well, I suppose I'll put it over here. I'm not sure how big this will get. This is minus I, minus 2I, minus 3I. Suppose we add, okay, so we'll do a couple. Suppose we add 1 plus I to, I don't know, let's just add it to plus 2I and see what we're doing here. First I'm going to put up 1 plus I. Here's the x component, here's the yi component, here's 1. This is 1 plus I. We know that, okay, so this is this. Here is the r here, it's the modulus of 1 plus I. The modulus will be the square root of 1 squared plus 1 squared. The coefficient for here, remember that if z equals a plus ib, the modulus of z equals the square root of a squared plus b squared. This b is really the coefficient in front of I. In this case, it's just 1, so don't try and make b squared be I squared, because that won't work. It'll give you the wrong answer. Technically, a is 1 and b is 1. It's right in front of the I, but we don't write 1 in usually. So this is equal to the square root of 2, and I think I'll put it up over here. So this is r is equal to the square root of 2. How would we write this in our polar form? Incidentally, this is called polar form. And when I come back tomorrow, I'll talk to you a little more about why it is. So we have this. This can be written as the square root of 2 e to the I. We already know that this is 1, 1. The tangent of this is going to be the rise over the run, which is 1. It's 45 degrees. I made it that way on purpose. I suppose I'll just put it as 45 degrees instead of pi over 4. Actually, no. This is something that will drive you nuts. You'll notice I wrote 45 degrees here. You have to use radian measure here because this was an infinite expansion. You can't use degrees in this. Yeah, I can see how that could irritate you. You'll get used to it. So now 2 plus I is the point right here. And this, so this is our first vector. This is our second vector. These both have length and direction. My producer tells me we got to load up another reel. Come back. It's going to be exciting.